morning, good afternoon, or good evening, depending on where it is you're listening. I'm Dan Turchin, InsightFinder CEO, and it's my pleasure to moderate today's discussion with one of the foremost AI researchers, who also happens to be our CTO and my friend. But before we get started with Helen, I thought I would share a bit of background, starting with a somewhat philosophical question. Why are we here? Well, in the case of AI for IT operations, we're here because our tiny little world got very complex over the last, say, 5+ years. Infrastructure is much more complex. There are many more data sources to be monitored. They often send conflicting messages, leading to a high volume of false positive alerts. New patterns are being introduced every day into our infrastructure, things like microservices and serverless architectures. And you know what happened is, even while all of the infrastructure around us got really, really complex, our ability as humans has not changed. So without literally adding 10x or 1,000x the resources to manage and monitor these infrastructures, we're faced with one of two decisions. We can either suffer greater downtime and always play catch up with the business and often miss SLAs and pay penalties, or we can look for a smarter way to manage infrastructure as it scales. And today what we're going to talk about is the latter of the two, the way to apply machine intelligence to essentially automate away a problem that was created in the first place by machines. Now, we're going to talk a bit about the value of closed loop change management, which has been kind of an elusive goal for many of us in this space for, say, at least 15 years. Now, Helen and her teams have published over 80 academic papers, and they're responsible for innovative technologies used by leaders at Google, IBM, Dell, Credit Suisse, and others. Helen was recently, she's too modest to talk about it, but was recently given the prestigious 10-year award from the Symposium on Cloud Computing for a paper that she and her co-authors published back in 2011 about elastic resource scaling. Helen's a professor at NC State, and she lectures frequently on topics related to anomaly detection and distributed systems. But before we hand over to Helen, let's open the time capsule just a bit. Roll back the clock about a decade. I remember in 2010 discussing this principle of what it means to achieve closed loop change management and auto remediation with the CIO of a large auto manufacturing company, and this was in Detroit. And we were talking about some of these same principles. What does it mean to wrap a layer of intelligence kind of horizontally across all of the key components in the life cycle? And I remember this like it was yesterday. Her name was Janice, and she looked at me in the eye, and she confidently committed that she was going to automate IT operations across the life cycle by the end of the year. Bless her soul. We need starry-eyed visionaries like that. The fact is, Janice's vision hasn't changed. Thankfully, our ability to deliver on the promise of self-healing infrastructure has. It's a bit about what we'll be discussing with Helen today. It turns out that with the right AI, systems can actually self-heal using pattern recognition to feed insights from anomaly detection through the rest of the life cycle, through incident management, problem management, change and configuration management. It can happen today because we have the right AI. That vision was powerful in 2010. It's just as powerful today. It was just about a decade ahead of its time. The right AI refers to not just the algorithms, but it's also the process of ingesting and storing and interpreting all that data. And when I think back to kind of Janice's vision from a decade ago, it's finally something that's commercially available. One of the things we're going to discuss today is what's the right set of questions to even ask to know where to start if you're early in your journey. Now, InsightFinder, we're proud to say, is built on innovations, many of which came from Helen's labs, that span hundreds of person years and multiple decades. We're going to talk a little bit about how that, quote, right approach to AI is being deployed at scale for some of the world's most complex banks, telcos, and consumer brands. I can say with confidence, you are in for a real treat. Without further ado, let's welcome today's guest, Helen. Good to have you here. I'm looking forward to this discussion. Let's start with a little bit about your background and how you got into this field.
Thanks, Dan. Hi, everyone. So thanks for joining today's session. It's really, I feel humbled to have this opportunity to share my personal story. So it's all actually, this journey started when I was a PhD student at the University of Illinois, Urbana-Champaign. And my advisor, Clara Neistat, is a very famous researcher in the field of quality service and multimedia. So quality service is actually an academic term for service level agreement or service level objective in industry. QoS has been actually a research topic for a long time before I entered the academia world. And multimedia is actually a very interesting application we focused on back then, because any short-term kind of like glitches will cause like big user dissatisfaction. So quality service is a very important aspect of this kind of application. And my vision at that time, my PhD research, is about actually provide a kind of distributed system. Back then, I call it the service overlay network. So that was 2001. So it's almost like 20 years ago. There's no concept of cloud. There's no concept of virtualization. Back then, there's only a concept called web service, right? And the vision I had for my PhD is that I will develop a distributed system that user can have arbitrary content. They can actually stream into this service overlay network, and you can compose the web services as demand. So, for example, the common application scenario I use is that you have a bunch of photos, and you can stream these photos into this service overlay network. And this overlay network will actually do some like image editing, automatic image editing, and then basically automatic categorization based on the content, and send a nice, organized, automatically generated, beautified photo album to you. So that was my vision like 20 years ago. Today is no longer kind of like imagination, it's reality, right? So the service called Instagram, and also Google Brain service for the Google Photo service. And also the infrastructure I was kind of imagining is basically cloud today. So the background is that, believe it or not, my first research paper is actually using neural network to predict, the bandwidth, available bandwidth on the mobile device, and also predict the user preference, right? And based on the weather, location, and your device, you can, using neural network to predict, what kind of like content, multimedia content you want to see on your device. So back then, of course, neural network is not as hot as today, right? So it's actually a cool topic. It's just because people don't believe neural network can produce the accurate enough predictions. And now today, a lot of things changed, right? So I think our vision did not change, but a lot of environment, and today we have much more powerful machines. We have tons of data, and also the other things that inspire me to do research in this area is that back then my passion is about building reliable distributed systems. And I remember the first keynote I heard in distributed system conference is delivered by Dr. Ephraim Spector, and he was the research head back then for IBM TJ Watson research. And he delivered a talk called Conundrum of Distributed Systems. So the conundrum is basically, we see people back then, right? People think, right, they can just have one server and they run the one web service, and then that's it. They can support all their customers. And however, since evolved, right now we all know like one server is not going to be used sufficient. You need the distributed systems. So as we put more functionality and scalability requirements to distributed system and more features, right? And the distributed system becomes more and more complex. That's just unavoidable kind of like, you know, trend. And as this complexity add on, and today we have like, you know, I would say hundreds of magnitude higher complexity than like 20 years ago, right? So we have virtualization, we have microservices, we have all kinds of like new features like AI, you know, stream, and all those things actually add up the complexity in the stack, right? So, you know, today you can see that we have like a lot of people talk about this full stack analysis. It's just because the stack becomes so complex. It's no longer just like, you know, operating system and application. There's actually all kinds of like middle layers, right, in between. So this is all basically inspires me to look into how to, you know, how to tackle this, you know, complexity. And machine learning is actually has been actually, you know, I just, you know, happened to get actually interested in that technology. But then later on, as we started more, then we see, okay, the machine data is actually particularly, you know, amenable for this machine, like new kind of machine learning algorithms, because we're dealing with tons of data. So we don't have problem, we don't have data. We have lots of data. That's not our problem. But the problem is that how do you grab insights from tons of data? So that's what kind of like eventually the whole research questions I have been asking myself all this time is how do we actually find the right insight out of this, like, you know, kind of like, you know, data, people call the data lake, right? I would say data ocean, right? So so that has been like my research for the past like 20 years. Yeah.
At what point did you realize that the work you were doing in academia might have broader commercial applications?
Yeah, that's also a very interesting story, and I never thought about starting a company. And so I've been in research lab. I worked at IBM Research before I joined the NC State. So I have been always in academia and has always been as a researcher and scientist. So we publish, you know, we have been extensively published papers in this area. So I remember our first kind of machine learning driven anomaly prediction paper was published back in 2006. So it was pretty early publication of using machine learning to do anomaly detection. So back then, I think people kind of like, even in academia world, people feel like, okay, this kind of technology is, you know, has value, but they don't feel like there's a big potential behind it, because people, they feel is that it's hard to achieve high accuracy. And second, people feel like, you know, even you have the prediction and let's say, you know, you have like 20 minutes or 30 minutes or an hour lead time, and a lot of problems are still handled manually, and they feel like, okay, you know, you know, this kind of like lead time is now very beneficial for them. And third is that, you know, there's not a lot of outages. Maybe, you know, 20 years ago, like, you know, if we just deal with one server, and probably one person can actually handle that, right? So you can have a machine, you can have a person to babysit a machine. So it was not actually catching a lot of kind of attention, but we keep on because we feel is that, you know, the data will become, you know, more and more, and the system becomes more and more complex. And I think that around that time also cloud computing starts to take off. So we believe that's the inevitable challenge we have to actually tackle. So we keep on working on that, and also we as many kind of like researchers in this field, right? So even today in commercial world, and people always start with supervised machine learning. And we also started with supervised machine learning. We used the decentralized Gaussian mixed model and Bayesian networks, all those well-known technology we tried, support vector machine. And so we can achieve some good results using supervised machine learning. But then so later on, once we keep on collaborating with industry people. For example, my research has been sponsored by Google, by IBM, also by Credit Suisse. So I worked with them together on some of the practical problems they encounter. And we quickly realized, okay, this supervised machine learning is really hard to apply in real world because machine data are highly fluctuating, and it's really hard to, correctly label data. Not mentioning it's very labor intensive to get those data labels, right? So you later need the person to actually tell the machine, oh, this is good data, this is bad data. So it's literally impractical. So we switched the gear and start to actually focus on unsupervised machine learning around 2010. And then we had our first set of results, right? So we from 2010 to 2011 until 2012, I think within around like 2 years period, we tried a lot of unsupervised machine learning algorithms, right? Like clustering, PCA, nearest neighbor. So and we get very bad results, right? So we keep getting bad results because it's a lot more challenging to use unsupervised machine learning to do this anomaly detection for distributed systems. The reason is that the distributed systems are highly dynamic, very fluctuating. There's a lot of dependencies in distributed systems. And so many machine learning models cannot capture those dependencies, cannot capture those, cannot, capture good patterns out of fluctuating data. So we tried a lot of things, and then we bumped into, so basically my PhD student, Daniel Dean, he actually, so he's a main kind of like a student who mainly works on this area with me. And he bumped into a research technique coming from kind of video tracking system. So the technique is called self-organizing map. So it's kind of a special neural network technology. It's still a neural network technology, but it's a little bit different from traditional multi-layer neural network technology. And it's typically used for tracking the paths of kind of automatic driving cars. For example, you can track the path and you can actually predict where the car will go. So and that's the original, actually, the usage of that technique. And we were thinking, okay, can we use that for system anomaly detection? And we tried for about like 5 months on this technique, and then we failed. It was very frustrating experience. And the reason is because we thought we can track the evolving paths of distributed systems just like we track a car. End up is not the case, because the system is highly kind of like unpredictable, in the sense that there's a lot of variations, there's a lot of context that is hard to actually quantify using this kind of simple neural network technology. So then we switch gear. We think, okay, can we use it in a different way to actually do that? And then, luckily, we actually come up with a way to actually adapt this kind of technology for anomaly detection. And then we published a paper back in 2012. And then our basically news reporters actually broadcasted the paper. Basically, they think this is a very interesting technology, right, with the cloud, with the reliability, with the AI. And so this news articles is read by many kind of leaders from industry. And I got calls from a lot of companies and saying, like, can we use it in real world? Because at that time, I think that's when the cloud took off. And if you guys remember back in 2011, AWS has a lot of outages. And one of the famous outage is that they have the, actually two in 2011. One is that they have a very broad service outage that caused Netflix went down on Christmas Eve. So that caused a lot of like news headlines. The other big outage is that they lost the whole US East region instances. So that's, when back then a lot of cloud service providers realized this is a big issue for them. So one of the companies actually contacted us is Google. And so I have been my research has been sponsored by Google. So I know people there. So I start to collaborate with them, and then after that, basically I spent the whole year at Google to evaluating the ideas in Google infrastructure, because at that time we only know this is the idea that works in the lab environment. We don't know whether it works in the real kind of production environments, and we never tried with the real world production data before going to Google. So after spending almost a year at Google, we tried over 20, 30 cloud outages in their production cloud environments. And we saw really very encouraging results. And so we see better than we expect accuracy. And also more importantly, we see is that we can achieve really good lead time. So in the lab environment, because we typically simulating the bug in the kind of very small test bed, right? Because we cannot afford a large test bed. But in Google, what happens is that we have, at that time we tested with all their infrastructure data. So they have tons of machines, tons of data, and a lot of production system. What we found out is that they have built-in redundancy. It's very complex, very highly redundant system. So you don't see one server went down and the whole service went down. You never see that. What you see is that the problem starts with a few machines, and then basically gradually propagates in their big infrastructure and eventually bring down the whole service. So this is basically where we can actually achieve very good lead time. So one of the outage we can achieve is even more than 24 hours lead time for them. They have sufficient time to react to it and to avoid a big service outage that bring down their production service for 7 days. So this is very encouraging, and so Google actually licensed the technology, and then then I got encouraged from NSF, my NSF manager, so the National Science Foundation, right? So essentially, I as a faculty, we always get sponsor. Majority of our support coming from National Science Foundation. And so luckily, National Science Foundation has actually a very good program called SBIR grant. So that allows basically, any researchers to commercialize their idea, their research prototype. So I actually got encouragement from the program manager, and I got grant from them. So we get our phase 1 grant, which is $150,000, not much. And then I realized, okay, maybe I can try to commercialize it. So I started a company back in 2016 after a kind of exciting journey at Google. So that's how InsightFinder got started. Yeah.
So I teased a little bit about the recent paper that received the Symposium on Cloud Computing 10-year award. Tell us a little bit about the research behind that.
Yeah, that's actually another collaboration we did with Google together. So the research started, I think it's around 2009. So that's basically, a year after I just get my academia career started. And back then, Google has a really nice program called the Google Faculty Award, and also Google Faculty Summit. So I met my collaborator, John Wickers, in that summit. And I was telling him my idea at that time is that, okay, cloud just got started. Back then, I don't think people have concerns about their cloud bill because they think, okay, I'm just rent one machine. Cloud is so cheap, right? 10 cents per hour. Okay, that's cheap. So, so they didn't realize, like, we did some math. We think, wait a second, if you actually run 1,000 machines and then for a year, you actually pay, hundreds of thousands of dollars on that. And the other thing for example, today when we talk to some of our customers, they pay like tens of millions of dollars to cloud service providers each year. So the cost is something like, a lot of people didn't realize back then, but then we did a projection on this and we realized, okay, there will be some concern on that. The other thing is that for me, I always like, so focus on optimization, right? So I work with some users and it bothers me is that their utilization is only like 7 or 10%. So they are paying like, 100% usage to cloud service provider, they only use 7%. And the other thing is that, in the traditional data center environment, right, before cloud is started, in the private data center, and we always hear like people talk about, oh, I don't have enough resources and I need the resources. And so back then there's a very common technique, right? So I believe everybody experiences, it's called overbooking. Right, airline doing that all the time, right? So sometimes you go to airline and say, oh, we ran out of seats. That's why the overbooking, and that's one way for the airline to make money, right? So they expect some people are not using their resources. So in private data center, they use this technique called overbooking as well. So it's actually quite effective to actually cut down the resource cost. But back then in cloud, there's no such technique. And the other thing is that since we started with prediction, and so we think, okay, when you actually do this kind of resource optimization, you can use prediction to guide your resource scaling, right? So particular back then, virtual machine migration just actually got it kind of like popular. So one of the things we observe, for example, when you try to migrate a virtual machine, and if you actually do that, trigger the migration before the host CPU reach very high level, let's say before 90%, before CPU reach 90%, you can finish a virtual machine migration in 10 seconds. However, if you actually trigger the migration after the host is already overloaded, let's say 95% CPU utilization, it took several hours to finish migration. So that's the power of prediction, right? I can give you maybe like just 10 seconds, 20 seconds lead time and allow you to trigger the migration before the CPU hits 90%. And you can get this done like seamlessly. But if you don't have prediction, you wait until the CPU reach 95%, you will never get this done because it takes hours to finish migration. So this is our motivation back then, and so we realized the power of prediction, and then and we realized that you have the technology to implement that. So we developed that, right? So back then, of course, none of the kind of commercial world, like cloud service provider has this kind of technique. There's auto scaling service, but this scaling service is actually not automatic. It's manual, right? User has to set the threshold and to trigger the migration. And a lot of times they don't know when they should set, what kind of threshold they should set. More importantly, it's still reactive. So this is basically, we started that. And then I think this year, basically that's 10 years, that marked the 10 years for this research paper. And the committee basically look at it is that the citations to the paper and the kind of the impact to the real world. So essentially, we look at the auto scaling service, actually the timeline in the commercial world. So in 2019, that's basically just last year, AWS released their first predictive auto scaling service. So it took, 9 years, right, for the idea to transition into real world. So we were very honored for getting this award, but it's definitely super rewarding for me personally to see some idea can generate real world impact.
So talking about that journey to commercializing the technology that came out of a research environment, so fast forward, so now you've commercialized some of the core technologies, and now you've introduced it to hundreds of customers around the world. Question is, what are some of the common mistakes that you've seen customers make when they're trying to adopt, whether it's anomaly detection or incident prediction?
Mm-hmm. Yeah, definitely. I think this has been a really hot area, and a lot of industry leaders look into this area. Many times for big enterprise companies, they hire data scientists to work together with their engineers to implement a certain kind of intelligent system management techniques, right? So the common problems that I saw is that basically is the understanding about assumptions, right? I think I'm in the research world, assumptions are always very important, because if you don't understand assumptions, you will have wrong application. So many machine learning algorithms has assumptions about the data. And that's where I saw the pitfalls, is that when engineers using those algorithms, they don't understand assumptions. For example, for the very simple technique, PCA, right? Principal component analysis. This is a very common technique used for dimensionality reduction. Because we talk about, for infrastructure data, machine data, you often deal with high dimensional data. So a lot of data scientists, they will recommend to you is saying, oh, you can use PCA to reduce dimensions, then you can improve the accuracy of anomaly detection. That's actually one of the common techniques we saw, also one of the techniques we tried at Google as well. The problem with PCA is that it has assumptions, right? The assumptions of PCA is actually pretty simple. The assumption is that the data among different dimensions has to be linearly correlated. So which means you can derive one dimension from the other dimension using a linear equation. So only when that linear correlation exists, PCA will be effective. Otherwise, PCA is not effective. So obviously, if you know these assumptions, you look at that machine data, right? So data scientist doesn't know, okay, my assumptions holds in machine data or not. But engineers, they know, right? They know the system. So if they look at their system, so wait a second, I don't see this linear correlation among my system metrics most of the time, right? So we all know system resources and performance are non-linear correlated. This is actually a well-known kind of like a symptom. So that's a fundamental problem, right? So then, data scientists knows the assumptions of the algorithms, and engineers knows assumptions of the data, and sometimes they don't talk to each other, right? Unless they actually knows, okay, this is something critical for me, and you need to validate it for me before I use it. But a lot of times people make, why it's called assumptions, people take it for granted, right? And the other thing, a very common mistake I saw is the clustering technique, right? So clustering is probably the most easy to use unsupervised machine learning techniques you can use for anomaly detection. So one of the biggest assumption for clustering is that you need to be able to distinguish two data samples based on Euclidean distance. That's the fundamental theory behind it, right? So if you have like two data samples, right, it could be a vectors, and if you can say, okay, this data sample is different from this data sample just based on Euclidean distance calculation, then you are good. But if you think about it in real world, like in machine data, if you look at the high dimensions, that they didn't realize this Euclidean distance calculation is based on assumptions that you don't have a lot of dimensions. right? So for clustering algorithm, pretty much if you have like more than 20 dimensions, your algorithm will no longer be accurate because Euclidean distance cannot capture the difference in this high dimensional data space. So this is also like, you know, again, assumptions, right? So and the other thing is that for data scientists, they don't understand basically some kind of like intrinsic dependencies between different machines and between different metrics. For example, a lot of times a common problem, so we just talked to one customer yesterday, and the data scientist actually raised a question to me. He said, okay, you know, one of the common things we found is that when the incident happens and we see a lot of system anomalies, system metrics exhibit anomalies. So how do I know which one is the principal ones? How do I know this is the you know, which the root cause, right? Because if you present all those anomalies to users and to operators, they will think like, you know, it's still useless because, you know, they don't know where to start from. And so if you understand the systems, then you will understand the intrinsic meanings of these metrics. For example, like, you know, if I tell you, okay, there's actually a one CPU metric, one load average metric, and if you know, so typically, you know, when you see anomalies in system metrics, in CPU metric, you will see anomalies in load average. And, you know, from data scientist's point of view, these two metrics are just two independent metrics. But from system researcher perspective, these two metrics are actually correlated because the load average is directly reflected. If you understand the meaning behind it, it's directly reflected, you know, by the CPU usage. So this is basically some, you know, intrinsic dependency information in the system and also in distributed systems, right? So we know, okay, which machine is, you know, depend on what machine. Those are basically kind of, you can easily derive from the domain knowledge of the application, right? And those information typically are not actually taken into account by the data scientists. So if you just apply those technology directly to the kind of machine problems, then you will bump into all kinds of problems, right? Low accuracy. And the other thing I saw common pitfall is that a lot of people heard about deep learning, right? So yeah, deep learning is very powerful. And, you know, if you have sufficient resources, if you, but one of the fundamental problem, the assumptions for deep learning is that you need to have labeled training data, and you need to have lots of training data. So if you don't have sufficient training data, and you won't be able to derive a good model. So once you have sufficient training data, yes, deep learning will be very powerful. So then the question is that in the real world, kind of like dynamic production environments, right? Particularly our recent research is about like how to do anomaly detection for containers, because containers are short-lived, right? So you start a container, you do maybe like a few minutes of operation, and you remove the container, right? Because it's so easy to start a container again. So because those short-lived transient behavior, it's really hard for actually any complex model like deep learning to capture those models. So those are the unique challenges for distributed systems to present to the machine learning world, right? And the other good example is basically, you know, another common prediction technique used by many companies called LSTM. So this is also kind of neural network technology, but then for that kind of system, and you know, it has to actually, you have to have a kind of relatively stable trend. So a well-known example is basically Facebook Prophet. So Facebook actually open source their prediction algorithms called Prophet. So I welcome everybody to try it. Behind it is basically some LSTM technology. So if you read that technology carefully, they said, okay, it works particularly well with kind of like metrics with seasonal patterns. That's because, if you have very highly fluctuating, highly dynamic time series data, LSTM won't work. Okay. So that's basically, there's for each machine learning models, they have their assumptions. And when you apply to them, you have to look at your data and ask yourself, are my data follow those assumptions, right? Otherwise, the machine learning algorithm won't work. The other thing also I want to mention is that a lot of people just gave up when they try once and it failed. Then they believe like machine learning doesn't work, right? So essentially, you can imagine no one shoes fits all, right? And so because we deal with such complex data space in kind of machine data world, you don't expect you have one technology works for all the data. And so you got to actually have a kind of ensemble techniques, right? So to actually figure out what kind of data you are deal with and use the right technique for the data. And these kind of things also has to be automated. You cannot rely on human to do that, right? So that's one of the common problem we saw our customer to deal with is that they have to actually rebuild model every time when they see a new data, and not mentioning calibrating the data model. Yeah.
So for everyone listening, that's Facebook's profit with a PH. Although we're all interested in Facebook's earnings, it's the PH and not the F. Just thought I'd make sure that got inserted into the recording. Helen, this has been great. We're about out of time, but I can't let you go without asking you one more important question. And that is, let's say, roll back the clock 10 years ago, you had this insight about the need for elastic resource scaling. And obviously 10 years later, it's as relevant as ever. Now polish your crystal ball and tell us what are the big ideas that you think will lead to technological breakthroughs, call it, for the next 5 to 10 years.
Mm-hmm. Yeah, definitely. I feel like machine learning is actually a kind of ideal technology for machine data analysis, right? So I couldn't imagine any other area for AI technology to take off, right? So we see like automatic driving, we see like image recognition, face recognition. Those are all kind of like and gaming, right? So those are all kind of like hot AI applications. However, I believe like IT operations, application DevOps is the perfect word for machine learning because we have so much data, and there's tons of insights, and our operators need help. And my husband is a software engineer, and sometimes he had to get up in the middle of the night to fix production bugs. I want to help him first, so I want to let people get the sleep back. Get time back to work on the problems that matters to them and they are most interested in. So and there's still a lot of open problems, and particularly my personal research interest recently is really zooming on this causal analysis. And I think in the machine learning world, I mean, anomaly detection is hard, but I think the causal analysis is really the fundamental kind of the hardest part of the whole space. And we had some recent research papers published in this area that can actually do automatic bug fixing. So by identify specific root causes and come up with the fix automatically. So for example, one of the most recent paper we published called the hand fix, we can actually fix those hand bugs in seconds. So this is actually, I think, a very exciting area. So there's a lot of I would say low-hanging fruits for people to tackle because we just have too many problems, and those problems are now going away. We fundamentally human writes code and human made mistakes, and those mistakes won't go away quickly. And also as we rely on this IT infrastructure more and more, and when very quickly those outages will soon mean life-threatening. So every minute, every second we can save for the for the user from the service outage, I think it will be extremely valuable. Yeah.
Helen, as that future becomes a reality, can I ask you to come back and talk more about the state of the art?
Sure, certainly, we'll be happy.
Good. Well, we're out of time for today. This has been fantastic. Hopefully everyone in the audience has learned a lot. We will have Helen back. We were just scratching the surface, but a fascinating discussion. For everyone that provided questions in the chat panel that we didn't get to, I promise we will get to them offline. Thank you for your time and attention. You see our contact information, both Helen's and mine. I will leave you with a quote that I think is as relevant today as it was 2 years ago, and it will probably even be more relevant 2 years from now. What can be predicted is better left to machines, but what requires intuition or empathy is better left to humans. So with that, if you're interested in learning more about InsightFinder, please go to that URL, InsightFinder.com/request-a-trial. We'd love to have you join our fast-growing user community, expose you to some of the technologies that Dr. Gu talked about on today's discussion. And with that said, thank you once again.